Hi. So in this video, we are going to look into how to run a simulation of a protein in water. Um, there are two ways to do it. First, if where we do the pre-processing in the GROMACS, and the secondly, we do the pre-processing using CharmGUI. So CharmGUI is an online platform, and GROMACS is all we know. And thirdly, how to do it using AI in Kapsid AI. So we will go through these three videos or these three part of videos. So in this video, we're going to cover the first part. In the next video, we're going to look into how to do the simulations using CharmGUI. And in the third video, we are going to look into how to do these simulations automatically using AI um, in using Kapsid AI. So yeah, let's get started. So to start with, we have to first find a protein for our system. So we'll go for our CSV and look for a protein here. So let's say we go for lysosome or lysozyme. Let's search lysozyme. It's one of the basic, really small proteins. It's not that long usually. So yeah, I think this looks good. Okay, so this have a accuracy of 2.9 Armstrong. We are trying to we will try to find something in the range of 1 to 2 Armstrong, within that range, not more than that, because sometimes you have some problems. So 1.9 is good, but I think we can find better. Okay, this looks actually pretty nice. It's a mutant um, at the 96th position, but that looks fine. 1.53 Armstrong. We will use this. So it's 3F1 IE5. I I think so. So we can just go download file, and okay, this have given me a CIF file, but we would like to have a legacy PDB format. So we now have this here. Just control all, and we'll just copy this whole thing. So now we have our protein file actually. So we'll now just cut everything, and we will go to our terminal. We will log into our account. So what you I would suggest you is that if you don't have an HPC account, you can create one with Uni Data Center. You can go back to the previous video and you can search in the video section. There is one video how to create one account here, so you can just go and create one account there. It's actually much faster and much convenient, and also pretty affordable, I would say. So I'll just log into my account. And why do I say that it's convenient? Because I don't have to install anything. You see there's like a lot of versions of GROMACS already available. um, and if I want to actually use one GROMACS version, you see, if I write GMX, it says command not found. But then if I want to use something, let's say I want to use this one, GROMACS 2023.3. So I'll just say module load GROMACS 2023.3. And now when I write gmx -h, you see GROMACS is already there, 2023.3. So it's really convenient, and it's really fast. Their services are quite good. That's why we use them. So let's create mkdir, or let's say we want to write protein protein or sorry, protein water. I think this is a good name. So we'll go to the protein water section, and here we need to actually create a new file. So whatever that thing was, we'll say prod.pdb, and inside this we will paste everything that we had. So now you see it's currently pasting, and if we look, there's a lot of water. Actually we need to clean that stuff. Oof. So, um, okay, I've actually accidentally haven't saved that, so I have to redo that again. We now have this. To save, we have to say quote WQ. I'm not sure if you can see the screen properly, so I'll just zoom in a bit. This is fine. Okay, so now we have this prod.pdb here at the end, as you can see, right? So yeah, what we can do here is use our GROMACS and then pdb to GMX, and then we pull the help and we look into what are the things we have. So we need to provide the pdb file in the -f flag. We have to provide the output pdb on the output grow structure using the -o flag. We and now here's these two other files, which is -p topology file and -i position restraint ITP. So these are all the outputs that will be generated. There are additional outputs that can be generated but are optional, as you can see here. And then we would like to use some of these other functions as well. For example, we would like to use IGNH, which is ignore hydrogen atoms that are in the coordinate file, which means all the hydrogen atoms in the PDB file will be ignored and they will be recreated. In this way, we will ensure that if there are some missing hydrogens, then they will be, replaced with new hydrogens. That's the way to do it. Then we can also use, let's say, this tir flag, which actually does if you want to do interactively the terminal selection, which means in the protein there are like two ends, right? So like it starts from some amino acid and it ends in some amino acid. So what happens is that let's say I want to change the groups from neutral to charged, or from charged to neutral, or from positive to negative, or whatever you want to do with it. If you want to change these beginning terminals and the end terminals, then you can use this tir flag. So I'll just show you how to do it. So gmx pdb to gmx, then -f, and we will provide the prod.pdb, and then -o we will provide prod.grow. Then we will provide -p, it should be topol.top, and then we can also provide the last one. What was that? -i. I think we can leave that. It will be automatically generated. So whatever name GROMACS want to give it, it will give that. There are two special flags that we wanted to use. One was -tir or -tir, and the other one was -ignh. Let's check if that's correct. So yeah, so here no means there no values need to be given after the flag, and I think it's same with the tir flag. Yes, so tir also doesn't need any other value after the flag. So this is the correct way to write it. We press enter, and now it asks if I have like which force field I would like to use. That's basically I have to provide. If you want to use any other force field other than this, let's say charm 36, charm 36M, or any amber force field that you would like to use that is not here, then you can just simply download that force field and put it in the working directory, and it will actually show up somewhere here at the top, that from the directory they have find or found one force field. So that can also be done if you want to use something other than what's given in the default. But this is very basic video. I would like to then follow with, let's say, charm 27. It's quite old, so we'll probably use that. So it's I have to just provide the number, which is 8, and I press enter. Now it says using charm 27 force field. Now it asks me to select a water model. I'll choose the first one, which is recommended, tip 3P. Now it asks me, since I've used that minus stir flag, so now it's asked me select the start terminus. So from where it is starting, there's a meth or I think methylene or something like that. And what do I want in the start? So do I want a charged group? Do I want a neutral group or nothing? So I'll probably use the charged one. So 0 for that, enter. And now in the end group, there's again a methylene. So it's very unusual. Both of them are same. Um, Oh, sorry. I'm really sorry. It says start terminus methylene 1, it's NH3 plus. Now I have to select an N terminus of its leucine at 164 position. So maybe I will use again the charged one. So I'll say 0. Um, okay. Okay. So apparently there are probably two chains. Yeah. Processing chain 2. As you can see here, it's processing another chain, which is chain B. So it's again asking me what I want to do with it. I'll do the same thing, 0 and 0. And don't tell me there is another chain. Yeah, there is. Aha. So this is going to be interesting. Chain processing chain 4 is this other chain, and we have ran into an error. So this is pretty common things when you're debugging simulations using the general method using GROMACS. You will find these errors a lot. So it says the residue in the chain do not have consistent type. The first residue name type ion, where residue this of other whatever. So basically what it's saying is that that you have other molecules than protein. And now what I mean with that is that you have these what I call them, this force fields. So you have these force fields, but these force fields are just for protein. If you have any other molecule other than protein, then most likely it's going to fail. So what do we do with that, right? So if you open one, so there are actually ways to do it. So let's first show you how to do it manually. So I opened VI, and then I can open prod.pdb, and I can start finding where this water molecule kind of starts, and from there I'll just clean off everything I want to. Oh, apparently there are a lot of molecules. Okay, great. So you see we have actually a lot of them. So there is these hmm, so there is these het atoms. As you can see, it's heteroatoms, and here it's for chlorine. Then it says Na, and then IPA, and there's a lot of things. But these are basically heteroatoms, and you see even water is being classified as heteroatom. So what we can do is let's say we can go and find. Okay, I think I'm lost. So from here onwards, I have to delete all the lines that are below this, right? So what I can do is there's one method with grep. I'll show you that in a second. But essentially what I can do manually is that I can write 10,000, which is like delete 10,000 lines from that point where I'm currently my cursor is, and then you press D. This happens in VI or Vim. If you're using any other text editor, probably this will not happen. So you can like select and delete something of that sort you can do. But Vim is quite nice. If you want, you can just comment in this video, and I'll probably make another video for Vim if you really need it, how to use Vim. So yeah. That's pretty basic and pretty old text editor, and it's quite useful for the Linux community. If you're using Linux on the very standard basis, I think you already know that. Okay, so I've now saved it. If I run the previous command again, let me just quickly do all the stuff quickly. So 8 and then 1, it's 0. I'm doing the same thing that I've done last time. So even if you don't follow up, then it's fine. So you see, now this have given us, you have successfully generated a topology from prod.pdb. Charm 27 force field and tip 3p water model are used, and done. Everything is correctly done. So if I look into the folder, this looks messy. To clean that, I would write rm, which means remove, and then I'll write hashtag, and then I press tab, then I press star. So the star is actually a wildcard. What it says is that delete everything after a hashtag. The way to write a hashtag is hashtag, and then you press star. So whatever file name starts with hash will be deleted. Press enter. I press ls again, and you see everything is gone. So all these hashtag files are basically backups that were generated. So they were the files that were generated in the previous error prone run, and then the moment I ran it again this time, all those files went to backup, and this is how the backup looks for GROMACS. So that's one way to do it. Okay, so now we kind of have that. What we can do is we can do the next step, which is to create a water box around the grow file. Before that, let's check how our prod.grow looks like. So there are about 10,000 atoms in the protein grow file, and this doesn't include anything else. There's no water molecules, there's no ions, there's no nothing, just the protein, and that's about 10,000 lines or 10,000 atoms, right? Um, and at the end, you see there's kind of a weird box that is already there, which is 7.83 nanometers, 5.6 nanometers, and 8.17 nanometers. But this box doesn't look cool to me. So what we will do is we will create our own box, let's say a cubic or rectangular box that we want to do. To do that, we have to use edit conf. I'll just okay, GMX edit conf, and then -h. This will give us the help. So here again, we have to provide some inputs, -f, -n, and -bf, but these two are optional, so we will just leave it for this video. Then there comes this -o flag, which is also optional if you want an output or not, depends on the kind of work you are doing. But we would kind of use one output here. And from here we would use this -bt flag, which says the box type. So there are 3 box type or 4 box types available: triclinic, cubic, dodecahedron, octahedron. Most of you would probably not need last 2 box types. It's kind of as you know, like dodecahedron is like, I think 20 faces or something like that. But yeah, I think for most of the users, triclinic and cubic is probably sufficient. So triclinic is basically rectangles where you can also modify the angles of these adjacent faces. So like a slanted rectangle, or double like slanted on that direction, this direction. So that's like a trapezium or something like that. That can be done with triclinic, and changing the angles here, you can do that. or if you use triclinic and you use 90 90 90, then you are into rectangle, or you can use a cubic, which is the most simple one, and probably that's what we're going to do. The other two, dodecahedron and octahedron, I'll show you the shapes, how it looks. Dodecahedron. So that's the, okay, so dodecahedron means 10, so decahedron means 10, and dodecahedron means 2 plus 10, which is something like 12. As I just read, I was wrong with 20 faces stuff. I thought 2 into, yeah, whatever. So so this is the shape of the simulation box you will get if you use dodecahedron. For curiosity purposes, I'm sure there are some people here who are actually curious, so please go ahead and try whatever you want to do with it. Yeah, the other one is octahedron. So that shape is like this. I think most of you have already seen this. So yeah. Okay. Um, is there anything else we can that we can use from this? I think center we can use, shift the geometrical center to XYZ coordinate. Or the other thing that we can do is center the molecule in the box. So whatever box it's going to generate, always keep the molecule or the center of the molecule in the center of the box. So that's kind of what is implied with minus C. We can use minus D flag, which is, let's say the protein is this big, and this whole camera frame that you can see here, it's like the box, simulation box, a rectangular box. So if this is the protein, what minus D flag will do is that the distance between, the protein and the box, that should be, longer. If let's say you kind of, I cannot increase the camera frame, but you get the idea, right? So what would be the distance between this end of the box and the protein? That you can change with minus D flag. So I think pretty much with these some basic flags, we can actually generate a pretty good, pretty robust simulation box. So let's do it. GMX edit conf. Then we can do minus F, and we'll see what else was there. Minus N, minus BF, not needed. Minus O. Okay, so minus F, we can give prod.grow. Minus O, we can give same box.grow. So basically, we are generating the simulation box right now. So it's just a name. You can give some other name as well. Then we can provide the box type and minus D and minus C. I think pretty much this would work. Box type I'm using cubic, minus D I'm using, let's say 1.2. So this 1.2 value actually signifies something. So just to say in short, let's say how simulation works. I'll probably make another video on this in more description. But let's say this is a simulation box and this is the protein, right? So what happens is that think of it as like parallel universes. So this whole thing actually have a same mirror image on the right and same mirror image on the left, and then on the top, and on the, like, the whole simulation box is copied multiple times, one on the left, one on the right, and one on the top, one on the bottom. These things looks like that. I'll probably show you at the end or in some other video how a simulation box looks, but this whole simulation box is not discrete, it's continuous with its mirror images. Um so what happens is that when you choose minus D equal to 1.2, then this next image which is on the top, that will be like 1.2, would be there 1.2, and then there would be this protein molecule, right? So between the mirror image and the protein there would be like 1.2 and 1.2 distance, which is about 2.4 nanometers. So this is kind of the regime where the long range forces, gets weakened out. If you have a D set to less than, this value 1.2 nanometers, then what will happen is that in your simulations you will see that this proteins, some chains, get are like attracted towards its own mirror image, and these are like artifacts. You will think that something interesting is happening, but it's basically just wrong simulations. So I would suggest using something like 1.5 nanometers, 1.8 nanometers if you really have that computational power. If you think you are on a budget, choose 1.2 as the minimum. Don't go below this at any cost. Okay, so then we have minus D set. There's another thing that we can actually choose from here, which is minus C. So what was minus C? Minus C was center the center of the molecule. So take the center of the molecule and put it in the center of the simulation box. So if this is a, let's say the system is creating a simulation box like this, the protein is here. So the system then, the code then actually finds what is the center of the molecule. This here, right? So it will just shift it here. If the protein was here, it will find the center here and it will put it in the center. So that's how it's kind of done. Okay, so I think it's pretty much done. So we'll press enter and it says now it have created the box for me. There are a couple of interesting information here, which is like what's the new center, what's like the system size or whatever. Where is this? Okay, they are doing, so this was like the previous stuff, and this is like the new center and the new box vector. So this is like the size of the box. So since we have chosen a cubicle box, is like width is 15 nanometers, height is 15 nanometers, and what's left, length is 15 nanometers, and the new volume is about this. So these are some of the things you would probably might want to log somewhere if you need it for some information later. Just keep a log, maintain a log for these, and that's fine. Moving to the next part, which is we have now made the simulation box. We now need to create or add water and ions to the system. So to add ions, we first need to have water in our system. At this moment, we don't have anything in there. We have only taken the protein. We have cleaned all the water and heteroatoms there. We put it into a box. Right now, the last step was putting it in the box. So we now have it in a box. But what next? Next part is interesting. We need to add water molecules. Like if there's the protein, there's all this empty space, water will be added. And what kind of water will be added? It's tip 3p, which is 3-point water model. Now, if you don't know the difference between 3-point water models, SPC, SPCE, tip 4p, like 4-point water models, then I'll highly suggest write me a comment here so that I know that you need a video on that. So I'll probably create one. So yeah, this basically answers pretty much most of our queries. Okay, so the next part, as I said, adding the water. So to do that, we can do GMX. What should we do? I think if I'm not wrong, it's called GMX Solvate. Oh, sorry, I was trying to bring stuff from my memory, which is very weak. So yeah, it works. So gmx solvate is the command to do that. Gmx solvate minus h, and this is again a lot of flags. Firstly, we need to provide minus cp, minus cs, um, minus p, and minus o. And then if you want to change the box vectors a little bit, then we can do that here, but we don't want to do that. All that stuff is already set in our previous step. So let's get started. So Firstly, with minus CP, we have to provide the structure file, which we have like new box or something. Acha, simbox.chrome. Now we have to provide CS. It should be spc216.grow. Let's just check. Yeah. So what is this? If you don't know what is this, again, write me whatever queries you have on the comment. I'll make a separate video on that, because in this video, if I just keep talking on stuff, then the primary video will get terribly wrong, like terribly long, which we don't want. Um, then, okay, CS is done. Now we have to provide the topology file. So topol.top, and lastly we have minus O, and we will just say solvated.grow. So here we not only have the simulation box, but inside the simulation box we have added water. So press enter, and it says everything worked pretty fine. It says output configuration contains 3,50,214 atoms and about 1,13,879 residues. For people watching from countries where it's counted in millions, then it's about 350,000 atoms and about 113,000 residues. You can also check the volume and densities. So yeah, pretty much that's it. Now what we can do is GMX. Okay, solvate part is done. We now need to add ions to our system. So before we go there, we need an MDP file. So one place that I know that all of you will get an MDP file is GROMACS tutorial page. It's one of the websites that's been created by, oh, don't tell me it's not there. That's interesting. Ah, now it's working. You guys are lucky. So this is one of these nice tutorials being created by Justin Lemkul. So shout out to him. So what you can do is you can go for his tutorial and look for this MDP file. I mean, whenever I teach to beginners, I kind of refer to this tutorial because it's really nice. You can learn a lot of stuff. So yeah, next part is adding ions. This should be somewhere here. So yeah, an example MDP can be downloaded here. You can press here, and this is the file that you need. So just copy this file from here. Again, paste one file here. So I can just, let's say, write ions.mdp, and I can paste it that here, save it. So now I have the MDP file. Now I can go for GMX. I think it's called GenIon, if I'm not wrong. Let's try minus help. Yes, it's right. Okay, so the command is GMX GenIon minus S, and I have to then provide a TPR file, which we don't have. So first we have to do GMX GROMP minus help. So this is a different command from GenIon. It's a GMX GROMP. So basically what GROMP does, it creates a run input file for GROMACS. So there are like a lot of steps in GROMACS that needs these run input files, and in all these steps GROMP is common. So just get used to using GROMP. So you have to probably use it 3-4 times during one simulation. So this is the GROMP part. It takes a lot. It can take a lot of input. Minus F GROMP MDP, which is we just downloaded in the name of ions.mdp. So minus F for that. Then minus C, we have to provide a configuration file. Probably I'm going to use the solvated.grow file. Then minus R for restrain. So we will again use that same file, which is solvated.gro. We probably don't need RB. We can skip the -n, it's optional. We can use the -p topology, and then rest we can also skip. Here also, instead of like this part is interesting, -o, and then there's nothing interesting. So yeah, so let's do it. -f, we are going to give ions.mdp, and we are going to generate. Okay, so I'm probably skipping something. So here I'm going to use solvated.gro -r solvated.gro, and now after that we will use the topol file. So topol.top, and after this I think there's nothing else. We can directly go for -o. We will name this as ions.tpr and nothing else. We can press enter, and it says this run will generate roughly 27 MB of data. So as you can read the line, it says this will generate. It haven't generated anything. It have just generated this ions.tpr file as an output, but that's not big. It says that when you run that tpr file, you will get 27 MB of file or so. So let's go into that part of running using genion. So if I go there and press help, so as you see, it starts from topol.tpr. So here it writes default value is topol.tpr, but our file name is ions.tpr. So we'll say genion -s ions.tpr, and then there is index file we can skip, it's optional. -p we will provide -p topol.top, then is -o or output. Since we are generating or we are adding ions to the system, we will name it ions, or let's say added ions dot grow. By this name we will keep on remembering that the ions has been added to this. So that part is done. If there anything else, okay, yeah, there's some interesting stuff here. So as flag wise, as you can see, it's -np, which is number of positive ions, minus p name, which is name of the positive ion, minus um, pq, which is charge of the positive ion, and then same thing for the negative ions, 3 is 3. And there are like some other fine-tuning stuff that you can do. Other than that, concentration can be interesting for you. For example, if let's say you don't want to put number of ions there, you don't know how many number of ions you would need, but you know that the experiment that you're trying to mimic in simulations have, let's say, 0.15 molar concentration or something, which is like 150 millimolar concentration. So that's like the standard, experimental conditions. If you want to have some salt concentration like that, then you can probably use that as well. The other useful command that I like is the neutral one, because your simulation needs to be neutral, else it gives artifacts while using some protocols in that. So I always recommend to put your system to neutral before doing simulations. So if you don't have this flag, then if you don't use this flag, then you have to manually set this by this number of ions. You have to like toggle around and find at what value the system will be neutral. But yeah, they have provided this neutral flag, so we'll probably use it. Okay. So in GenIron, so I'm not using these ones. There's pretty nasty ones. You can use that if you really need. But I'm going to use these two, which is neutral and like putting the concentration. So I'm going to use 0.15. Just to be sure, here 0.15 means 150 millimolar concentration, or um, you can say that this concentration flag takes all the values in molar quantities or mole per liters. So if your concentration is in millimolars, and you saw that there's been written 150 or 200 millimolar concentration, and don't put 200 here. You have to put 0.2 here. Then if you have 200 millimolar concentration, this is an important one. And then uh, neutral. Okay, so let's press enter, and now it asks select a continuous group of solvent molecules. So the app is not really knowledgeable enough to know what are the solvent molecules and what are the non-solvent molecules. So what it basically does is that, let's say there are like 1 million solvent molecules there. What it does is that this program actually finds one solvent molecule, kind of knocks it off, and replaces it with a ion molecule there. So it uses that protocol to add ions randomly in the whole system. So that's why it needs the information on what are the solvent molecules, so that it doesn't knock off a protein molecule or some other molecule that you have there. So let's say I'm going to use this group 13, which is sol. Here the water group is also the same. So, but yeah, I'm going to be consistent with my naming, so I'll just use group 13. And it says, you see, replacing solvent molecules with da 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 with chlorine. And if we look on the top, there's also Na. So basically the salt concentration that they have added by default, because I have not mentioned what kind of salt I want. So by default they've used NaCl. Um, if let's say you want to use KCl, or you want to use some other salt, you can just name that, and it will use that salt if that salt is available in the what do you call that? Um, Again, my memory is bad. What do you call this? Like if I run this PDB to GMX, the force field, yes. So if that force field contains that salt, then you're good to go. But there are, just mind you that there are some salts not available, like MgCl or you know AgCl. These are some of the things that are not available. You have to just check for yourself if what salt you are using, and if that salt is available in your force field. If you don't have that, there are a couple of blogs that tell about how to add a new salt type, but these are like pro level stuff. So because I understand that this video is meant to be for beginners, you don't have to worry about that for now. Just use plain NaCl and you know get to learn things. When you are when you have learned a lot of stuff in GROMACS and in other simulation tools, you'd probably get these things pretty easy to add stuff and other things. So now JNIN has been done. We have really got a simulation box with a protein inside that, a lot of water molecules on side, and a lot of ions as well there. But the problem is these have been added randomly with random configurations, so they are not equilibrated. They are not in a way that it's you know in a good posture with the protein, like it's not favorably solvated and stuff like that. So what we need to do is we need to first do an energy minimization. Once that part is done, we then go for, let's say, two rounds of equilibration. So these equilibration are like short molecular dynamic simulations, like very short molecular dynamic simulations. The purpose here is to put the water molecules in the proper posture around around the protein, such that the energies are not high enough, like for the system to crash. So basically all we want is favorable energy favorable interaction energy, or yeah, whatever. Okay, so now the next step is actually energy minimization. Before we go into that, we would need another MDP file. So we will go here and we'll try to find where is that energy minimization. It should be somewhere here. Um, Here is this input parameter. You open that. That's the energy minimization file. So basically, don't think that these are like static files. You can add a lot of stuff, you can remove a lot of stuff, but this is something that Justin Lemkel have already developed or already given as the basic parameters that always work. So I'm just copying it from here such that you guys can also follow this path and copy these files. Else I would have used my own MDP files, but then it would be hard for you to cope up with this video. So for that sake I'm using this. So I can then, let me first create another directory. So you see it's a directory shown here. So we will now go inside the directory and we will create a new file em.mdp. So I'll paste my stuff here. Now I'll go back to the previous directory and I'll say gmx grom minus help. So we have to again take the grom help. So where is that grom stuff? Yeah. So now again we have to do a lot of those stuff that we have already done, but this time the names will be different. So I'll just keep the names that should be same, and what should be changed, I'm just changing that. Now the em.mdp is inside the em folder, so I'm writing it em then slash and then em.mdp. Then I have to provide a structure file. This time my structure file has changed. This time my structure file needs to be the one that the ions are already added, right? So I'll say added ions.grow. Again here as well the same, added ions.grow, and at the end my name should be em and then em.tpr, the output file, and I press enter. This again says 27 MB of data, whatever. We are going to now run using MD run. Last time we have used GenIron because we wanted to add some stuff, but this time we are using MD run. So this is the module that actually runs simulations. So let's check the help section again. There is a lot and lot of flags in here. So for the shortest, I'll just talk about that. What are the least amount of flags you need to use, such that you can get your stuff going. So the first thing I like to use is the defenum. So defenum means default name. So default name, what it does is that there's like a lot of these input files. There's like a lot of input files are there and a lot of output files are there. So what that default name does, it kind of takes the TPR file name and it uses it across the all the input and output files that are needed. Secondly, you would need to use for now it's actually nothing. Whatever is needed, it's actually needed on the like the equilibration and simulation part. So I'll just talk about that when I will be doing that. So at this moment I'll just say md1 minus def nm, and then the name of the tpr file, which is em. So I'll not provide the full name, which is em.tpr. I'll just say em. So this is the name of the file, and this is the folder where it is. So I'll just provide the full path and then just the name. If you provide that like .tpr after this, it will fail because it asked for default name. It just wanted the name, and it kind of assumes that the input file, which is em.tpr, having the same name em, right? You kind of get the idea. Now if I just press enter, it should start energy minimization. Here we go. Okay, one more thing, which is as you saw that there's nothing else was happening there. If you want to see what's happening, then you can just provide -v. It's called verbose, which means now your system will start throwing a lot of stuff what's happening there. And as you can see, something is running, but this is slow. There are a number of steps, like 50,000 number of steps going to happen, and this is 30, right? So it's a lot of time going to be taken. What we are going to do is we are going to check if some job is running. So there is no job is running, so we can use some of the faster nodes, like whatever we were running so far was on the login node, and this should not be done. Login node are just for logging in and doing some petty works, like what we were doing, like adding ions, um, doing solvation, adding some water molecules, doing ions and stuff like that. These are like small works that you kind of do on login node. But most of the stuff that need like something like energy minimization, doing solvation, like sorry, doing equilibration, production runs, these needs to be done on faster, really speedy nodes. So to check what kind of nodes we have here in this account, so let's see node info. So there are about two type of nodes here. One is red, which have about 32 vCPU, 64 GB RAM, 16,000 CUDA cores, 24 GB VRAM. It's currently idle and the cost is just 60 rupees per hour. And I'll just show you the speed in a moment. And I think this energy minimization will take like, I don't know, 0.002 dollars or something like that. So yeah, pretty much worth it, I would say. So as you see, we have a very nice GPU here with 16,000 CUDA cores. So let's just see how fast we can actually get it done. So for that, we need to first create a um, bash script or bash job submission script. If you don't know what it is, then please go to another video that is on the channel. Go check it out first. You will get an idea about how to submit jobs on this platform. So yeah, so I'm assuming in this moment that you have already seen that video and came back here. So for creating a job script, I need to first line needs to be bin bash, and then the second line needs to be having some information. So and then I need to submit what are the modules I need to use. So if you remember from the start of the video, that I've kind of done something of this sort of command on the terminal so that I can use the GROMACS. Same thing needs to be put here as well so that the script can use GROMACS. So that's kind of the idea. GMX md run, and then def nm, then em/em, then -v. So that's kind of the job script is ready. Here this partition red means I want to run in this kind of nodes. So that kind of nodes will be used, this red ones, because that's more faster. And if we now run as batch, and if we check, our job is running. Submitted jobs is 887, 887 is here, and Kapsid is running. If we check again, it's still running, 10 seconds. We can put a watch command there, -n1, and you can see our energy minimization is running. So once it is done, and here it is done, 22 seconds, right? 50,000 steps in 22 seconds is much faster. If you remember from here, this thing took like, I don't know, 30 seconds or so. We just waited. So yeah, let's check what are the files that we have. So inside this we have this em.log. So inside the em folder there's em.log file there, and if we go to the end of the file, it says the maximum force that is remaining, the potential energy that is there, and see it's in minus, so looks good to me. Everything looks actually quite nice. Let's see how many steps that been run. Okay, so the system has converged somewhere around 1800 steps. Sorry, yeah, 1800 steps. So yeah, that kind of looks good to us. We can now run what do we call it? So energy minimization is done. Now we need to, so what happens in energy minimization is that, let's say there's some water molecules. The water molecule looks like this, right? Hydrogen, oxygen, and hydrogen. And let's say there's this protein kind of stuff there. And if, let's say, there's a clash between water molecules and the protein, then what happens after that, right? There's like huge energy gain from that clash. So that kind of bad clashes are being corrected in energy minimization, but still a large portion of water molecules are not arranged properly so that they can have favorable energy. So that can be actually corrected using equilibration steps. So before running an equilibration step, we will again go back to the website and we'll try to find an MDP file for that. So keep our eyes open. Here it is, the MDP file, and looks, this time the MDP file is quite bigger because we are running a proper simulation, and this is supposed to be bigger, right? And you can actually add much more information in there if you really want to. There's like a lot of parameters that you can tweak in simulations. Okay, so again we'll create a mkdir equal 1. So I'm just naming a folder equilibration 1 or equal 1 in short form. And what we'll do is we'll create inside this folder we will create another file, which is, let's call it nvt.mdp. Why do we call it nvt? Because the mdp file I've copied, it actually does keep these let me just show you. So you see here it is written pressure coupling is off, and p couple it's set to no, which means pressure coupling is not happening, right? What does that mean? That pressure would not stay constant. So what pressure coupling and what temperature coupling does, it kind of provides a barostat and thermostat around the system. It's like an imaginary code that maintains the temperature for temperature coupling, kind of maintains the temperature of the system. It's kind of an imaginary code actually that keeps the temperature at a constant value. Think of it of something like that. But if you want to have a practical like practical correspondence, then think of this as there's a system inside a jar. Let's say there is this system, right? Whatever is inside this, and you put it inside a bowl, and this bowl is with water at 35 degrees centigrade. So that's a constant temperature, and somehow magically, let's say this is at minus 15 degrees centigrade. If you put that bowl in that, uh, and just assume that this water, whatever water is inside this bowl, that never gets colder. It always stays in 15 degrees. So what will happen? Um, Somehow this temperature will slowly come down to 15 degrees centigrade, and it will stay, oh, sorry, I think it was 35 in the beginning I said. So it will come to 35 degrees centigrade. It will come to 35 degrees centigrade when placed in the bowl, and it will like the inside temperature will be maintained at 35 degrees centigrade. So that's kind of the ideology of thermostat. Similarly for barostat, it um, keeps the pressure in control. So in this system, we are using, we are using the temperature coupling in this MDP parameter, but we are not using the pressure coupling, which means the pressure will not be constant, but the temperature will be constant. And if you know, let's say a basic statistical mechanics, then you know, then we have these, NVT, NPT, and then NVE, these kind of equilibration systems. So yeah, N here means number of molecules, which is kind of constant in our system because like there's like bang on, I can count the number of atoms in our system, right? It was somewhere like 300,000 or something like that. So we kind of know the exact amount of atoms in there, and no atom is like, going away. It's always going to be inside that simulation box. So the number of atoms are constant. For V, it says the volume stays constant and the temperature stays constant. And on the opposite, when you use both temperature coupling and pressure coupling, you keep the number of molecules constant, you keep the number of, sorry, the pressure constant, and you keep the temperature constant. So that's how it is done. Okay, enough talking. Let's get back to our GROMP. So that was the previous command. So minus F, we can add equal 1, and then we can add NV. Oops, I think I have not saved that thing. So now I've saved it. Um, so let's try to write it again. Equal 1, and then nvt.ndp for, okay, now for um, the structure file, we can add, what do you call that? I have already run the energy minimization, so I'm going to use em.chrome. Here as well, I'm going to use em/em.chrome. Then there's topol file, and then there's here the output needs to be in the equal 1 nvt.tpr. So that's kind of the GROM statement should look like. We press enter and we get a good output. It says it will now generate about 834 MB of data. So it's a pretty large file, I would say, for energy, sorry, for equilibration. So, but we will generate it, no worries. GMX, okay, I think that part is already done, right? So we now need to go to the run.sh file, and here we will create this equal 1, and then oops, nvt. I think that is done. The other thing I will just add is minus nb gpu minus update gpu. So basically these are like two more flags from the MD run here. This MD run have these flags. Basically what it does, the first one does is that it runs the non-bonded calculations on the GPU. If you don't know what is non-bonded, go and read about force fields. In the force fields, force field can be classified into bonded groups, like bonded calculations, non-bonded calculations, and more. Just go and read there. So all these non-bonded type of calculations that happens in the force field, that happens in GPU only. So that's what this flag means. Update means that the whole code will be GPU resident. What is GPU resident? Probably not needed for this video, but I'll just give you a reading material if that helps. So if you go to their websites and kind of find the blog section, here go to the GROMACS section, and here, so kind of they have found this blog here. It's pretty interesting. So if let's say you use on the same system, like they have tried it on the same system, if you use NB CPU, bonded CPU, which means both of these calculations happening on the CPU, and also the PME part is also happening on the CPU, then you get about 170. I'm not sure if you can see this. Then you get like doing all this stuff in CPU, you get a speed of 117 nanoseconds per day. If you do the NB GPU, bonded GPU, and PME GPU on like now all these three calculations are done in the GPU, it gives about 544 nanoseconds per day, but explicitly mentioned that the command needs to be controlled from CPU, like it's not GPU resident. The whole code won't run on the GPU, but the instructions will be sent to GPU by the CPU, right? That's what update CPU means. Then the speed is about 544 nanoseconds. But then when you use, let's say, NB GPU and you use update GPU, then you get 728 nanoseconds on the same system, right? So why not kind of use GPU resident always if your system allows? So I kind of personally prefer to run, both NB GPU because that's like the most heavy computationally, and then I also have the update GPU. So like if you just combine these two, you pretty much get speeds around this. Okay. So you kind of have put both of that there. I'll just submit this job. Let's check. Yeah, it's running. Watch, and you can see that it's now running. So yeah, let's wait for this job to finish. Once that is finished, I'll restart. I'll just cut this video here, and I'll start it from there then. Okay, so I think I don't need to stop that video. It's already done. So we'll just check how fast we are getting stuff. Based on that, I'll decide if need to actually run the other parts or not. So let's see. And you see we are getting a speed of about hmm, so the speed currently says is 153 nanoseconds per day, right? So yeah, let's then move on to our next part, which is generating whoops. Oh, sorry. I think I need to name it equal to, and then GMX gromp. So I can just name it. Now this will be NPT because I already know. This will be from equal 1. This will be nvt.grow equal 1 nvt.grow, and then at the output it will be equal to npt.tpr. Press enter. It says cannot find the npt.tp because I haven't copied that yet. We have to again go back to the source and we have to find that stuff. Where is it? So we need the npt actually. Probably it's in the next page. Okay, here it is. After finding for 30 seconds, we have found that. Again, it's pretty large. We'll just copy that, and in the equal to, I'll npt dot mdp. I'll just paste that here, save it. Okay, let's also get a tour of what these parameter means, right? So we are using an integrator. It's an MD integrator. Oh, wait a minute. What I'll do, I'll create a separate video for describing MDP parameters. I think that would be better, such that because this video is already getting long, I don't want you to stay here. So I think that's what I will do. Just check for another video. I think I'll post it after this. Okay. So what I'll do, I'll just run that crom statement again. Now it says it will again generate about 800 MBs of data. We will now change the run statement equal to npt. I think this is fine. Just as batch.run. So yeah, this is running. As you see, it's this is running. So let's just wait for, I think it was a few more seconds, and then I should be getting the stuff. As per my previous experience on the same system, for 300,000 atoms, I should be getting a speed of about 130 nanoseconds per day. Yeah, that's kind of the speed. So yeah, let's see. I think that's what we were getting previously. I forgot the number that showed up last time. I think it should be something like this. That's what my chart says. So okay, this is finished. Great. Okay, if we now look into equal to pt.grow. Whoops, I wanted to go into logs. And you see, okay, I was expecting 130 nanoseconds, but we're getting about 150 nanoseconds per day, which is pretty fine. I can actually, okay, after this, I'll probably not take your time longer. After this, there would be another step, which would be equal, let's call it MD only. So MD slash, or I like to call it prod or production run, right? These ones are like longer runs. I probably not run this now because it will take a lot of time. So what I'll do, I'll just show you until the gromp command, how to generate that, and after that it's just like sbatch submit, right? So I think probably you can do that. So um, so if you look here, I need that MDP file. It's here. So just copy this MDP file and create mkdir prod vi. Um, let's call it md dot mdp, and this should be inside that prod folder. Paste your stuff here, save it, and what I can do is gromp. Let's go to gromp. Now the md.mdp is inside the prod folder. We go to equal to, we go to npt.grow. This is equal to npt.grow, and then output would be in the prod md.tpr. You press enter, you get this time you get about 195 MB of data, which is nice. I think the reason here is because we are not md.mdp. The reason here is that this is not generating a lot of simulation. So this whole n step and the dt determines how long the simulation would be. And currently they have set it to 1 nanosecond, which is very, very, very small. The kind of simulations we do here is like 1000 nanoseconds, really long, like 1000 times larger simulations than what is currently being done here. So you get an idea, right? So, and then if you run that kind of simulation, you put 1000 after this. So if you put 10 here, then it becomes 2 GB. You put one more zero, then it becomes 20 GB, and then you put one more zero, then it becomes 200 GB. So one production run of this lysozyme quadruple structure then actually generates 200 GB of data. So you get an idea how big these files would be. So yeah, what now I can do is, let's say, since I have made the file, all you need to do is you just need to say sbatch run.sh, press enter, and your job is running. But I'm not going to let it run because it will probably run for a few minutes depending on 150 nanoseconds per day, which means 150 nanoseconds in 24 hours. If you do the math, it will be some minutes, I don't know. So I'll cancel this, but if you just let it run, then your simulation is done. Congratulations, you have done your first simulation, as I assume. If you're doing it in your laptop, God bless you. I don't want to emphasize it a lot, but please do not do it on your personal laptops. It will burn, so it's really not recommended. So what I'll do is I just cancel 890, and it's not there anymore. So you can cancel jobs like this. I'll, if you want, I'll create another video on how to run jobs on Slurm. I think that would be helpful for you guys. But yeah, if you like this video, please share it with your friends, or put a like and put a comment maybe, so that I know that it's really worth doing what I'm doing here. So yeah, thank you so much. If you need any other help on any other topics, you can just let me know. I'll probably make or try to make a video on that. Right? So thank you so much. Bye bye.